system, you have everything on one piece of silicon. So it is an era of mixed signal system domain where analog is also there, digital is also there, memory is also there, IO pads are also there, power management circuits are, everything is there on a single piece of silicon. So it is a era of mixed signal system domain. So you should understand that you cannot only design a digital chip, you cannot only design an analog chip. So you should not be. So rather we should know how to put two things together onto one silicon piece. So VLSI design issues are known to you. Basics will be your digital electronics that you do in your first degree. Here it would be analog electronics or microelectronics. Rather, I would say microelectronics is the base for that. Because analog electronics, what we teach here is normally that we have the ICs available and how do we create circuits around those ICs. This is what I understand by analog electronics. Unless you specifically look at PLLs or A to D converters. So analog electronics is how to make use of the ICs. How can you build circuits using ICs? Various types of ICs are there. Microelectronics where you actually start playing with the devices. Okay, so device is there, how to build a circuit using that device. So that is what is actually a circuit level design. And because VLSI is nothing but a mass scale design strategy. You design millions and millions of circuits in one go, and you design millions and millions of circuits in one chip. It's a mass scale production technology. So here complexity is going to be tremendous. A lot of complexity, like a lot of transistors, so many interconnections, so many devices, so many capacitors, resistors, they all are put onto 1 centimeter by 1 centimeter chip. Okay, so numbers are huge. And because the numbers are huge, manual design is totally not feasible at all. A designer cannot start designing a circuit manually using a paper and pencil. So you start with an idea in your mind, maybe you can do some preliminary calculations on a piece of paper using a pencil, and then ultimately you have to resort to EDA supports. The electronic design automation tools that we require, and we need to design our circuits over there. Initially, this technology, IC technology, which was invented in 1958, the first IC was made in 1958. It was actually made for mass scale production. And digital was one such domain which immediately took the best of this technology. It immediately adapts itself very well to the technology. And hence, initial few decades, till 80s, you can say, initially 20-25 years, they were dominated by digital design. This technology was dominated by, or very too much used by the digital designs. Those were the eras where we have having hybrid ICs or hybrid PCBs, like a PCB where you have an analog chip, you have a digital chip, you have a memory chip, you have external connections, you have external, so everything put on one PCB and a system is made. Okay, so that was an era of PCB design where we had different chips. So analog chip is there, or a battery chip is there, or memory chip is there. So they were all different chips were taken together, which are compatible with each other in terms of IO pads or IO signals, and then they are put together on a PCB and connections are made appropriately. This was how the designs were done. But now what happened that recently, because then the moment you have an off-chip computation or off-chip communication, one chip to next chip, there's a delay involved, a lot of delay is involved. So to make systems very fast, my chip can be operating at a very high rate, but it is because of these off-chip communications that speed was getting limited. Because off-chip communication cannot be very fast depending on the capacitive loading that comes due to IO pads. As a result, people thought, let me do away with off-chip communication. Let me bring everything into the same chip. And that is where the SoC starts coming into picture. So we have everything now on a single piece. So it is a single piece itself is a single design. It's not a PCB that I take a hybrid system and I keep on putting them and then soldering them or making connections. No, it's not like that. Okay. And because of this, the SoC system came into picture. So now the speed also becomes very, very high because there was no off-chip memories, or sorry, off-chip communications. So as a result, we are talking of mixed signal systems. So nowadays everything is on mixed signal systems. So we never speak of a single analog or single digital. So what is happening is that analog, initial 2 decades were devoted to digital design, but then there were applications which started coming up where people tried to find a solution, and that was mainly in the field of healthcare. So biological systems, people started designing chips for biological systems, like the electronic eye, electronic nose. Okay, so similarly neuromorphic designs, which are where the chips are placed inside the body and then signals are taken, pacemakers. Okay, so body compatible designing started coming up, and where that was mainly in the arena of healthcare, and there was a huge revolution that came up, and VLSI had to adapt to that evolution, electronic industry, and that is where the analog importance was felt, because earlier no application was towards the healthcare or biomedical systems. Now because of this area opening up and there was a huge demand and huge applications, analog design became very, very important. That was the one reason that analog designers, suddenly there was a spurt in the demand of analog designers or analog expertise at that time. So slowly VLSI shifted towards analog domains. It's not that digital was totally left behind. Digital was always there. People, they were now expert because 20 years, 25 years experience they were having in digital design. So they were already adept at designing digital systems, and they know all the issues that may come up during designs, and they have found out the ways for that. But now analog was something a very difficult, a new domain at that time in 90s, late 80s and early 90s, where analog demand was felt. And because very few people were working in those areas, so there was less expertise available, so huge research started happening in that area. Everybody started gearing towards the research in that area, and very soon lot of papers came up, new designs techniques came up, various ways of avoiding various issues or problems, drawbacks in our design that came up. Huge research funding was available in that time. 90s, you can say, was dominated by the analog design. But yes, digital was always there. It's not that we left digital completely and then we moved on to analog. No, this cannot happen because digital technology is something that is very well adapted for high-speed processing. So we could not leave digital as such and moved on to analog. No, and that's the reason that in 2000 onwards it was mixed signal systems. People started designing both the systems together so leveraging the best qualities of both the domains. So wherever digital was best, digital block is taken. Wherever analog is best, analog block is taken. A very good example of this is a sigma delta A to D converter, which is a combination of analog and digital. Otherwise, your flash ADC, your pipeline ADC, they are more or less dominated by analog designs. But sigma delta was one application where data conversion, it has shifted from, or partly done by analog and partly done by the analog and digital techniques. Similarly, PLLs, similarly phase lock loops. So there were many systems they came up, and people found that with mixing this or adopting to this kind of a technology or this kind of an approach, they could design better systems, high-speed systems, reliable systems, and more flexible systems. So it was possible. As a result, the SOC took off. And now there were various variations of SOC that came up. And nowadays people are even talking of a system in a package, SIP design, which is, you can say, a more modified and advanced version of a kind of SOC. Okay, so in this course, we shall be learning the basics. Now I will not cover the basics. As I said, microelectronic circuit is a base for this. So whatever we have done over there, I assume that you people know. But since you are from different universities, so what is the level that you have been taught, I don't know. So a little bit of revisions I will do. But I expect you to do some homework on your own, because I cannot cover everything in the class. I know I'm not saying that I am teaching this course just to cover the course content. No, I want you to understand. But something that we assume that you people have a basic knowledge. So you need to refresh it time to time. Okay, so you have to help each other. You have to take help from the internet, or you can, if you wish, you can, if I give you some references, you can go through and learn on your own. You can always ask questions. I welcome all of you to ask questions. Even a very basic question, don't feel hesitated. Because if a simple thing you are not understanding, the more complex thing that I will build on that, you will certainly not understand. Okay, so don't hesitate, please ask. It may be a very trivial question. You may feel others will laugh at you. Don't worry, and do not give a damn to that. If people are laughing, let them laugh, but you should ask. Or if you feel hesitant in speaking up over here, come to my chamber, drop me an email, get a time, or just have a talk with me on phone. But please do that. One thing, so before I start discussing the handout, evaluation content, the course description, one thing I want from both the campuses is that you have to send me an email. I'll be putting all my notices on Nalanda. Okay, so to access that, I need to include your mails and IDs. I need to pass it on to the person in charge over there. So one of you should make a distribution list of all of you. Okay, email distribution list, both your BITS Pilani ID number as well as the Gmail ID number. Okay, you have to make it and send it to me. Now I request one of you to take the responsibility. Who will take? I first of all, before I assign a person over, let me find if there is any volunteer. Yes, I need one person volunteering from the Goa campus, one person volunteering from the Pilani. Your name is? Manish. Your name is? And from Goa campus? Who will do this?
Yes, I will do.
Yes. So I want a complete distribution list, emails distribution list. Okay. Give sent to me in this week. Manish from the Pilani campus, and who's the, may I know the name?
Nisarg.
Nisarg.
Yes, ma'am.
Okay. So Nisarg from the Goa campus. Okay. So you will be sending me the complete data of all the students. Currently, I haven't got the list from ARCD, so I'll be using the data that you would be supplying to me. All the assignments, all the notices, all the lecture slides will be put on Nalanda. So till Nalanda is active, I will be sending the slide to one of the people and I request you to share. Manish may be one person, and girls, I can have one girl, Apurva. Send me your email IDs. I will be sending you the slide so that you can share it. Your responsibility will be to send it to all the others. Okay, no girl, no boy, he should come to me, madam, I haven't received the slides, or I haven't received the information. Please develop this habit of sharing between Pilani and Goa campus students. Please share the information. Okay, same thing I'm talking to the Goa campus also. Share whatever information you are getting to Pilani campus. Keep talking to each other. Keep guiding each other. If there's an issue in EDA tools, Pilani people know, share it with Goa campus. Same thing, if Goa persons know, students know, they should share it with the Pilani campus students. So you are just one class. Do not assume that they are different and you are different. Don't think like that. A single class. 29 students, single one class, and share. Develop this habit of sharing with each other. Do not keep information to yourself. If you know something, share it. Okay? And if you feel that this is something madam should advertise on Nalanda, come discuss with me and send me the document. I'll put up on the Nalanda. Clear? If you know something, just write a small document, send it to me, I'll put it on Nalanda. So sharing is something that this habit you should all develop. Okay? So the students, I can see Shruti over here. Most of the things for you would be little bit of repetitions because you have done the first degree course ADVD. For others, maybe 90% would be new and 10% would be repetition. So frequency response is something that I request all of you to go through and have a complete revision, because this is one thing that we would be using very well, very frequently in this course. Because And to understand a system, we have to understand the frequency response completely. Linearity, non-linearity, everything will be understood from the point of view of the frequency response. Okay? You are formally registered in this course? No, informally. Okay. So, as I said, many things will be just a repetition for you. Okay? So, you may take your own decisions. So, this is, I am the instructor in charge. So, let me first discuss the handout that we have. Just go, I think this handout copy is available on the ID website. So, I have listed the textbook and number of reference books which are available in our library. You may also find a soft copy of that on net, possibly. I don't know how do you do, but I have found students having a soft copy of all the books. Okay, so you may find, you may refer to, because all these are good books and they all discuss the same concept but in a different manner, because authors, they have their own approaches. So whichever way you find it's easy for you to understand, you can go for it. And then there would be a number of research papers that you would be required to go through to understand the current state of design research in this area. Course plan would be somewhat like this. There would be brief introduction, then switch single stage, a revision. This is a kind of a revision that I will be doing. I will not spend too many lectures on that. Okay? And then source coupled as a differential amplifier, advanced current biasing, noise, operational amplifiers, comparators and latches, switch capacitor circuits. Okay? And if possible, I will give you an overview of the complete mixed signal systems like A to D and D to A converters. The complete system, it is a subsystem. So starting from very basics, we will try to move on to the system level design, which is a complete A to D system. Okay. And then there would be evaluation. There was a mid-semester test, 25 marks weightage, 90 minutes duration. Then there would be analog design project, and there would be weekly laboratory assignments. Total 40 marks will be spread throughout the semester. They will be all open book. Mid-semester test will also be open book, and comprehensive will be of 35 marks, closed book. Total comes out to be 100. I will assign a 3-week slot for you weekly in OLAB so that you can come. I will give you assignments, take-home assignments. It is not a structured lab, remember. I will be giving you take-home laboratory assignments which you can come in that slot. Not come, rather all of you have to come in that slot. 3-hour slot dedicatedly for you only in the OLAB so that you can come and do it. Apart from that, you may also come at night to finish it off. Okay? But then in that 3-hour slot, you assume that it is a structured lab. Though it is not. It is not there in the timetable, but I want you to take it as a seriously structured lab. Okay, so dedicatedly 3 hours, 2 to 5, I will book the lab for you so that you can come and do your assignments, take home assignments which will be evaluated. And there will be a regular attendance taken. I will make one person responsible for taking the attendance regularly. Same arrangement I require and I want, if possible, at the Goa campus also. I hope the instructor over there can talk to me and we can finalize on some kind of an arrangement where people get dedicated 3 hours, maybe after 5 or maybe 3 to 6, whatever is convenient to them, depending on their busyness throughout the day. But then I need them to really work for these assignments. These are made such that you gain something in every assignment, a knowledge which can use for further doing your analog project in this area. That would be given to you. So one assignments would be over, some 5-6 assignments would be given to you, then a design project would be given to you. Okay, so that design project, it's not that whatever I am giving you, that's the only thing you have to do. Rather, you have to read a lot. You all have to read a lot. Consult the recent publications. Come up with the best design. Okay? And if you really do it well, there are 2 opportunities. You can use this work of yours either to send it for a conference paper or there's a cadence design contest where you can send this as one of your entries. Okay, so do not just think it is an analog design project. No, rather take it as one opportunity which can open up or which can lead to a new opportunity where you can have a published paper, or you can possibly go for a cadence design contest, and possibly you may win also. Okay, so use this opportunity and think in that direction. So whatever I am giving you may be one part, you can add something more to it to make it more viable, to make it more better, and to make it more useful. So your innovations are also going to be evaluated. In what way you have thought about new ways? Your innovation, what's your innovation part? What's your creativity? That is something that I would be looking at. Okay. So very clearly, let us go through its introduction phase in this class, or let us just try to have an overview of this analog domain, VLSI design in analog domain. So very quickly we will go through, look at the growth of analog design. So in process, so nowadays, even at 32 nanometer, design is still being done. It's not that technology node is shrinking or reducing. No, so analog design is becoming difficult. Yes, it is becoming difficult, yet designers are designing analog circuits even here. So there are ways, there are techniques people they have found out, and they are finding it out even now, which can be used for analog designs. So starting from a single microprocessor that was developed somewhere in 1970, we have moved to multi-core SoC. And in this, there is a sizable chunk of it is analog portion. Okay. So performance requirement has become nearly 10 cross. 10 times performance, you can say. In one decade, rather I would say in the span has got reduced. Okay. So Pentium 2 processor to Core i7 processor, you can see the technology node has changed from 250 nanometers to 45 nanometers, and speed has tremendously increased from 400 megahertz to 3 gigahertz. Now think of analog circuit which is operating at 3 gigahertz. It is not easy. It's very difficult to achieve that speed, but yet we are able to achieve it. Okay. So the systems are really going very, very fast, yet they are low on energy. I think a lot of creativity, you should appreciate the creativity of the designers, that they have been able to reach at this stage. And they are not stopping here, they are moving forward even further, making the systems better and better. Okay, finding out design ways. Technology has its own impact. Technology creates or gives you more leverage, better systems, better devices. I agree. But then designing creativity is something that really has an impact. Making systems more flexible, more intelligent. Think of a cognitive domain, cognitive circuits, where you really try to function like a brain. Okay, you have kind of perception, you perceive. It's an ability that only humans have. We perceive things in advance. Okay, this might happen. Now you are trying to put this functionality on a chip. This ability on a chip, your circuits are becoming more intelligent. Perception. If change is happening, adapt itself. This is what humans do. This is what we humans do. So bringing this cognitive ability onto the chip, biomedical systems, is something that now you can say man is trying to emulate God in a small way. I won't say in a big way, in a small way. So bringing such ability on a chip is something that is really, that requires a lot of creativity, lot of innovation, lot of thinking. You cannot create systems just like that. So you should appreciate the creativity of the designers. And analog circuits will keep on growing, because now the focus is on giving a tailor-made solutions for consumer electronics. Your mobiles are tailor-made nowadays. What do you want? You have that kind of a system available to you. You can choose. What do you want? Accordingly, get a solution. So consumer-focused electronics, tailor-made solutions. And then, next is the speed. Very fast. Let me show you. I think this is all consumer-focused electronics in great demand. This is an example of a handset, that mobile that you have. The slide shows you the basic structure of a, which has three main blocks. One for communication, getting, sending the signals with an antenna. Then there is a baseband processing, and then there is a power or the battery management. Basically 3 blocks. Okay, and it requires a huge amount of processing. So look, convert the voice signal to digital stream. Okay, so before conversion you need to filter it. So whatever you are getting, you need a DAC for that, if you need to filter it out. And then there is an analog filter to clean up the signal and remove the noise from that. So it may look like a very single block, but within that block there are too many modules and sub-modules. You can keep on breaking it down. And as you break it down, you will try to find out, okay, this is going to be, this small block I can do in digital and this block I can do in analog. So this way is known as a hierarchy. It's going to be a hierarchical kind of a system. So where we know, okay, top-down approach, what we want, and then keep on slowly implementing it till you reach the lowest level of hardware implementation. So main block, then sub-blocks. Each sub-block has its own modules. Each module has its own sub-modules, and everything in the last comes as a circuit on a chip. Ultimately, that is a physical realization. But your function is decided by the system. Okay, so that system has its own specs, own specifications. So as I said, power amplifiers are there, RF carriers, analog circuitry to ramp the signals up and down, to control the power. Look here, so much analog things are there. So putting the signal up on the airwave generally requires turning bits into modulated carriers. You need again a DACs, you again need filters. Receiver side, you need ADCs. You need something we call it as the PLLs to receive the bits from the signal. Time synchronization is done. So decomposing the signal into quadrature components. There are so many communication. Look, can you see that major application of VLSI is into communication? Major application is into communication. That is one area where VLSI is tremendously used. Similarly, next area is your consumer-focused electronics. Your small things that you use daily life in your TV set. TV is also a kind of a communication only. Your washing machine, your mixer grinder. Inside there is always a small chip inside which is controlling everything. These are all consumer electronics, area of consumer electronics, and third can be healthcare. So you are surrounded by VLSI from from all the sides. And every system is going to be a mixed signal system. So let me not go through all this. I want you people to just go through, otherwise this will take a lot of time. So these are all the reasons why analog is still very viable. And people, they are going for analog design. So high speed is second reason. We want our processors to, or our tasks to be done very fast. Don't want to wait. Okay. So as I said, it takes so many audio, video, RF and applications to make our daily life routine very simple and electronically controlled. So this slide shows so many applications that are mainly analog in nature. So this is small signal amplifiers, RF power amplifiers, disk drive, read-write circuitry, motor controls, line drivers, receivers, transmitters. These are all mainly analog in nature. Okay, so this slide just shows that you cannot live without analog. It's just not possible. And one major reason is that whatever you may do, your entire system can be digital possibly. But when you communicate with your worldly signals, they are always analog in nature. You have to have A to D converters. The signals analog signals or the word signals or your surrounding signals, they have to be converted into digital stream, and then only it can be processed by a digital chip. But whatever you are getting as an output from the digital chip again has to be converted back to analog, because otherwise, suppose it is an audio amplifier, you cannot hear. Output streams, your ear cannot understand the streams, bit streams. It has to be converted back to analog. The word is analog in nature. All your pressure, temperature, earthquake signals, they are all analog in nature. Voice, analog in nature. So we just cannot think of not designing any analog system. People, they say, go for digital. Reason is noise immunity. Lot of noise margin. No need to worry about the so many bit values, because there is only 2 bits, high or low. Don't worry about too much of signal variation in the voltages. Do not think of the swings or the Q point stabilization. Nothing is required. So all these criteria that I am discussing, they make analog design very complex. But then you cannot live in this world without the analog signals. So processing can be done inside digitally, but ultimately they have to be converted to analog. So there is a kind of eggshell analogy, eggshell, like the eggshell. Inside the shell, it is all digital, and outside the shell, it is all analog. So shell is an interface between analog world and the digital chip. And now even in the inside of the shell, roughly 20-30% is analog. It is not only digital, mainly because of this cognitive intelligence systems you want to develop. There you have to go for biomedical system. You have to have analog content over there. So analog is something very, very important, and you cannot ignore it if you want the entire system to work. So here we will use this fundamentals. I will teach you all the fundamentals. Mostly we go for a kind of intuitive design, so that we assume or we perceive things, that I use my fundamentals knowledge and try to perceive that the effect of any change that I am making in a system on the total performance of the system. Okay, so this is what we try to do it, and there is a tool also which helps us in this, which we call as an analog HDL tool. Okay, this also helps us. We do the entire system in analog HDL system tool that is available in Cadence, and then we just take up one block and design it in multiple ways. And every time I go on changing the block design and try to see the effect on the final output. So this way, usually people did it earlier using MATLAB. They used to do it using MATLAB, but nowadays even the VLSI EDA tools, they have made this facility available. Even you can interface between MATLAB and EDA tools. Even that interfacing is also possible. So that you can make the best of both the softwares. So for analog, there is something called analog HDL, where you can change one system or one block of a system and see the impact on the total output, where other blocks are remaining, or design of other blocks are remaining the same. So fine, this is what we will be looking at. This is something that you should all understand, the bandwidth versus applications. But normally a good idea of this chart gives you a very clear idea where analog would be required and where digital would be required. So somewhere here, if I show you one slide, if I have, where is that slide? Just give me some time. I'll give you one slide before I discuss this slide. Oh yes, this one. Now look here. This is 100 mega signal frequency. Okay, so roughly below 100 mega, it is mostly digital. Okay, and above 100 mega, so 100 mega is not a strict borderline. You can say it is a range. It is a range. Okay, so there's a hazy range. So broadly we can say above 100 mega, it is mostly analog implementation. So all applications which are below 100 mega or 50-60 megahertz, we mainly use digital processing. Okay, and if you go above that, analog applications are mostly used, and in between this range, it can be a mixed signal systems. Okay. Now let us go back. So technology versus applications. This is where we were. Yes. So look here, telecommunications, starting from 10K till 1 giga. Telecommunication, all these applications, they fall within this range. Okay. Now look here, AM, FM radio, TV, it roughly from 50K to 1 giga. Optical communications above 1 giga. This would be mainly the analog systems range. Microwave, RF, they are all into analog domain. Video, acoustic imaging, seismic signals processing, sonar, only audio. So audio now can be purely digital. So a good idea of this will be necessary for you to understand what you are designing and why you are designing, for what range you are designing. Okay. And then naturally, when you work, there are two things that you take, and then you take the two inputs and then produce a successful solution. Designers, this is a designer. This part is designer. So he understands what technology he is going to use for his system and what are the benefits of that technology that he can leverage. So he understands the technology, what are the drawbacks and the advantages of this technology, and for what function he is designing the system. So these two inputs he requires, put them together, uses his own creativity and try to find out a successful solution. We all know that this is the only way of doing it. So designer's space is something that nobody can replace it. Okay? Technology may be there, function application may be there, but if there is no one to combine the two together, there would be no successful solutions. Analog digital circuits comparison, I think you can go on your own. Okay. And then unique features, geometry is very important, remember. In analog, normally it is a full custom design. When we say full custom means mostly the layouts are done by the designers. So there is no semi-custom design where you have a complete tool which can do the entire layout on its own. Okay. So here you have to draw the layouts on your. So geometry is very, very important. So it is a full custom design and geometry is very important. So it takes a lot of time in designing the system. Even the layout is done by mostly the designers. There are standard teams in every company who does the very critical layouts on their own. Okay. So skills are required, and then the design flow remains the same, starting from the specifications. And every time you go to the next step, then come back to the same previous step to check the results. And if the results are not coming to your satisfaction, you redesign. So the IC design flow does not change much. Okay. So let us see some useful tips that normally followed in the industry. That if you can do something in digital, don't unnecessarily go for analog. If something can be done very well in digital, do not unnecessarily go for analog, because analogs we all know it's going to be a little bit more complex. Why to spend extra time and extra effort when you have a very low effort solution available? Okay. And if you have a possibility of copying, that's something you can replicate without actually designing it all over again. Remember, we need to cut down on design time. We need to cut down on design effort. So if something can be replicated, that will save a lot of design effort, because then you need not redesign it. It's only replication. So if you can replicate or copy, then go for it. It's not a bad thing to do copying. Okay, it's not bad thing here, because you are saving on design time, you are saving on the design effort. And if you cannot copy it, then you have to design it. And if you are designing it, then you have to apply certain good practices, which are called as a thumb rules in designing. Do not avoid them, because the moment you avoid them, who has framed those good practices? It is the designers who failed multiple times and then came up with a successful solution. So in that process, they learn something and then they jot down these successful tips. Okay, do it. You will always get a successful solution. So you should adhere to good practices. Clear? If you want to just avoid those multiple failures once again, because people they have already gone through, why should you try to go through the same process again and again? Let us learn from the previous mistakes. Okay? So apply good design practices, and if you can't fix it, suppose you are not able to find out a solution for a particular problem, then advertise it. Why? Because you make it public. Why should you make it public? Let somebody else work on it and try to find a solution. Do not keep it to yourself. Do not keep it to yourself. If you have found out something, even then you also publish. Because let others take the benefit of what you have found. So share it. Share it. That is why the forums are there. If you find there are so many forums, there are so many student forums are there, engineer forums are there. They keep on sharing their experiences with each other. Because this is very much necessary. And this is maybe one of the reasons this technology has gained so much over such a little span of time. Sharing was done. Nobody was keeping the information to himself. It was a publish. The moment you get something, it was published. Even if you are not able to get something, advertise. Say, I am not able to get the result. Can you provide me with the results? Let somebody else work on it. Okay? So this is the eggshell analogy. Fine. So this I have discussed already. So these are some of the trends that people they have found over the years. Okay. So design complexity, can you see? So depending on the application, design complexity changes. So can you say for the ASIC, the design complexity is around from 1K till approximately 1 million transistors, approximately. Okay. So 1000 to 1 million transistors. Normally it is in this range ASICs are developed, and only for digital applications it is even higher. Number of transistors, because digital is something that IC technology has adapted itself. So technology, because initial thrust was on digital design, so technology which was developed, it was developed for digital design. Okay. But later on people found no, analog is also used. So analog they started designing using the same technology which was geared for, which was best suited for digital. So they did not develop a different technology for analog. No, the same technology they started using. And because it was not best suited for analog, so what they did was that they found innovative designs. Because technology was not best suited for analog. So there was a flaw. So what they tried to fill this gap by finding out innovative design solutions. So as a result, analog and digital, they are able to put together in a one single system design. That's the reason. So architecture, technology is also important, but the way you design, that is also very important. So technology is something where designer has no role. A designer has no role. It is because of the technology, the MOS going to 32 nanometer, the MOS scaled down to 28 nanometers. You are not doing anything. As a designer, I am not doing anything over there. I am only using it. Because it is a better technology, I get more reliable systems, I get more smaller systems, I get more cheaper systems, I get more functional systems, more complex systems. I am not doing anything over here. Same design that I was doing in 38 nanometers, I can adapt it to 28 nanometers. I am not doing anything. It is simply a change from technology node to next technology node. I have not done anything. But the moment you start changing the design, here is the contribution of the designer. This is the research in design. So do not only depend on technology. Technology will give you 10 cross improvement. Let your architectures also change. So that together will give you say around 50 cross improvement. So put your contribution also. Innovative design solutions. Okay. This is the process trends. So roughly every 2 years you are getting a new process generation. Okay. This is the yield. So for different technology nodes, 90 nanometer, 65 nanometer, can you find the defect density is going low over the years? 2005 it has reached this value, 65 nanometer even less. Defect density is going low. This is the next node, 45 nanometers, it has reached here. So this is a 2 years, roughly 2 years gap. Roughly 2 years gap. Okay, so as defect density is reducing, that means higher chip yield. Yield is increasing. Yield is increasing. Has the bell, has the time over? No, we have time? 2 5 minutes. Okay. So Moore's law, it's a Bible of VLSI design. Like a verse from a Bible, that every 18 months, the integration density will double itself. Something that is taken very seriously by the designers, though it was only an observation, but now everybody believes in it. Moore's law says it can happen, so it can happen. We will work for it, it will happen. And because they work for it, it gets happen. Because they work for it, they believe in it. They believe, you don't know, Moore saying it can happen, so I understand it can happen, so let me work for it. Because they work for it, it gets happen. But Moore's law is something that everybody believes very firmly in that. That every 18 years integration density will double itself. And that's the reason we have started from 50 micrometer and we have reached 45 nanometers. Same reason, because of that. Okay? So this is something that I want all of you, I will putting up this slide. The moment I get all the emails, I will forward this slide to all of you. Okay? Go through it, it is just an introduction. I have not yet started anything concrete. So next lecture now will be to give you or to revise the basic single stage amplifiers. That you all, I request you all to go through so that we can quickly go through. Need not spend too much of a time on that. Don't want to spend too much time. So quickly go through all the 3 stages, folded cascode, differential pair, so that we can quickly found a base, make a base, and then move on towards operational amplifiers.